Hi, thanks for joining me on this presentation. What is the thing saying, chat? Oh, that's a doc thing.
Sorry.
No problem. Thanks for joining me on this presentation where I want to show an idea that occurred to me of how we might be able to do either backups or cold storage or some sort of replication of Git repositories where the bulk of the data is stored in object storage. So this is sort of a solution looking for a problem. So maybe that's a bad thing, but I want to share it anyway. And it's based, there's a merge request for this, and I forgot the link. Where's the merge request? I should have that in here. This is the merge request, 1244. And so do I demo it first, or do I talk you through the code? I think I should demo it first, unless there are objections. Okay, so what am I going to do? I have a little setup here where I made a tree where I have something representing the GitLab server, something representing the object storage, and something where a user will be having a checkout of a repo where the user is going to push. And I just put a repo here, which happens to be the Gitaly repo, but that's not really relevant because the only thing that's relevant is its size. So let's clone that repo. I hope this is readable. So now I have, I can pretend I'm a user over here in this window. This window is in the directory where the repo is stored, and this window is the directory where we make snapshots, and right now it's empty. So let's make, let's start with making an initial snapshot because the user doesn't really, the repo already exists here. So for that, we have this gitly create bundle command. For initial snapshot, it takes no input. And then I want that to go to the storage directory. And let's call that 000 full. And what did I just do wrong? It's gitly bundle create. Okay, now we have the initial snapshot, and it is about 17 megabytes. And now let's say users are using this repo and they're pushing stuff. So let's create a commit here on the right. I think I still have that in my history. Yes, empty commit. So that's just going to be a very small push, just one object. And now here I can make a new snapshot. And what does that look like? So now the new snapshot is based on the previous one. This is one of the main ideas here. So that would be the 000 snapshot. I need this one. And that's going to be a new file. And let's call it incremental. And now we have two files here. And I can keep going like this. I can also make a snapshot if nothing changed. Then let's start from 1 and create 2. Now we have 3 snapshots. And we can replicate these snapshots somewhere else. So let's do that here in the replica directory. I have nothing here yet. I want to create an empty repo with git init. Go in there. And now use the Gitaly bundle apply command, and the input will be the first thing. And now I have a repo. Let's see. Git fsck, stuff is here. That looks good. You can do git for each ref. There's a bunch of refs. So I just replicated that first snapshot. And I can apply the other snapshots on top of it. And I can try to do that in a fancy way. Let's see, ..storage, repo.git, and then I want the files. I want to sort that. And I don't want the zeros. Okay, this is not, I'm not going to do it the fancy way. I'm just going to do it the simple way. So now I'm going to apply the second snapshot. And what changed here is that I pushed this one commit. I updated master. So let's see. The master was at 7 DEB first. Let's double check that. So I ran git for each ref here. I should have deleted stuff. I think this is the one where I ran for each ref. And it's at 7 DEB. And now if I do git ref parse master, again, it is at 041, which is that one I just made. So that got replicated. And then there was the last snapshot that was empty, and I can also replay that, even though it's not very, it's not going to change anything. And now I applied that last snapshot. So that is the demo where I'm just doing stuff and not explaining what's going on. Any questions so far?
What's going on?
Okay. Yeah, so what is going on? There's two commands. There's the command that creates the snapshot, and there's the command that retrieves the snapshots. So one thing we can do is look at those commands. Another thing we can do is look at the snapshots. Let's just look at a snapshot. So this first one is a full snapshot. And my text editor is not going to like me for it, but this is what's in there. It starts with a list of all the object IDs and references. And this looks better if you have a monospaced font. There. So this is just object IDs and references. And then at some point, there's an empty line and then a big blob of binary git back file data starts. And my text editor needs a moment to search there because this is not the best text editor for loading large files. And this format is very, very similar to the Git bundle format. The way the refs are at the top is slightly different, but this idea of having the empty line in there comes from the Git bundle format.
Why aren't we using the bundle format?
Because the bundle format doesn't let you deal with ref deletions in a nice way. I can explain that better when I get to the design of the. Okay, let's explain a little bit better what's going on here. This list here is the output of git for each ref. So this is a full dump of the ref database of the repo we're snapshotting. And you find this in each of these snapshots. They always have a full dump of the ref database. And that seems a bit excessive, but it's from a git transport point of view, that's actually normal because every time you do a git fetch or a git push, you get a full dump of the ref database from the server. That's for the HTTP protocol, that's called the info refs request. And because this is a full dump, we can easily see if things got deleted. Because if something is not in this list and it currently exists in the repo, then we know we can delete it. And with the normal Git bundle format, it won't tell you about the deletion in a reliable way. I'm not explaining this well, but it's roughly about things like this. Yeah, so that's the format. And in this last one, there was no pack file data because nothing changed. So that was just text. And how do we create these? Or do we want to see more about the format? And the format is just an example. I think there's things one could do to make it nicer, but this just seemed to work and it gets the point across. So let's look at the script that creates this. I happen to write this as a shell script, which is maybe a bad idea, maybe a good idea, I'm not sure. So this creates the snapshot. What does it do? It first, and it creates a snapshot to stand it out. It first writes the name, the header of the file type. And then it runs git for each ref to take a single dump of the ref database, and that goes into a temp file that I called ref snapshots. It's very important that we use one single ref dump, because otherwise, if the refs change while we're doing stuff, we can get weird inconsistencies. So we take a single dump of the ref database, and we give that to getback objects, which tells getback objects that we want to, sorry, this one is the top of the file. This is the empty line. So let me get another file up here again. So this line gets created here. And then all this stuff gets created here via for each ref into T. And then there's an empty line. And that was at the end. Here's the empty line. That's echo. So then we're this far, and then there's a bunch of binary data. And the binary data is created by getback objects, which is a git plumbing command that is the foundation of both the back file format used on disk and of the git transport that we use when we fetch and push.
Hey, Jakob, does it matter if new information's been added between the ref snapshot and the packing?
Well, that just gets ignored.
Because it won't have a reference and it'll be dangling.
Yeah, okay. It's only going to, so this list here at the top, this and these names are irrelevant to pack objects. These object IDs are what will be the inputs. Let me just show you the input of getback objects. I think that will, I can just edit this. And sheets. So now I'm not using getback objects, I'm just going into cat. So now we can see what goes into standard in of getback objects. And let's try to create another snapshot. And we have 2, so let's make 3, 2. And this is going to now output a lot of data. No, why not? Didn't I just save that file? Oh, that's because I redirected it. So this is the redirected output. So first you have, again, the list of the object names and the ref names. And then the empty line. And here begins the input to getback objects. And this is just a repetition of the same object names. So here we have 03C, 549. If I go back to the top, then you see that here too. So these are the things that we're telling getback objects that we want. And then a little while down begins a list of things that we don't need. And these start with caret. So this is the general idea. This is the thing we feed into getback objects, and then getback objects computes a pack file that must include these and need not include those things. It may include some of these if it doesn't. It's not forbidden to put these things in there, but it tries to avoid putting these in there, and that gives you the small pack files. So that's really what we're feeding into the thing. And then let me rename this, because this shouldn't be called this. So that's the input example. So how does that get created? Well, this is why it's maybe not so good that this is a shell script, because it's a bunch of awk stuff. This line takes that ref dump and prints the first column, which is the object IDs. So if we look again at this example, it prints $1, which is this thing, and $2 would be this thing. And it's doing that out of the cached copy we made of the ref dump. And then comes the slightly more complex part, where we have an awk command that quits if it sees an empty line. So that means that if we have something like this one, which is data in it, we want, wait, 102. This one. This one has data in it, and because of the this thing will exit when it's here, and that effectively means that to create the new snapshot, we only read the head of the old snapshot, and that allows us to just use a single blob for the whole process, because we just read some data from the head, and then we were done. We close the file, and we don't care anymore. And that would also translate to something that's stored remotely. So that is that thing. Then if the line doesn't start with a hash, then we print the first part. So that is, it's printing all these things, and it's skipping this line. That's what this regex is about. And then it's possible that some of these objects no longer exist locally. So we pipe it through a git cat file batch check to see if these exist. And if the word missing is not there, then we print these things with a caret in front. So unnecessarily terse awk fun. And that's all that happens. So that creates that list that I showed in this file in the input example. So first all these object IDs and these things with the carets, and that is the input that git back objects then uses to create an incremental pack file. Still with me? Going too fast? Going too slow?
I think I'm getting it a little bit. So just to clarify, it's incremental because the pack file is generated from the previous ref log that's captured. Is the essence of it? Okay.
Yeah, it's important for this to work. It's important that we know what the previous one is, and that because if you want to reapply this and something was added in the middle that is not in one of the previous ones, then you're going to get a connectivity problem. So it's really a log, and it has to be a linear structure where you consume them again in the right order. So I could now move on and show the part where we unpack these, just to see how that looks like. It's not very surprising. It's just the same ideas in the opposite order. And I wrote that in Go because half of the file is binary, and parsing binary in shell scripts is no fun. So I'm just using Go. So what is this doing? It is using buffered IO because otherwise you have no way of pulling this off. It looks for the header that we remember. Then it reads the top of the file and creates a map. And what does this thing do? It reads lines. It looks for an empty line. If it sees an empty line, it breaks. So that's this thing, again, about the format where it looks for this line. If it sees that, it breaks. It does a split, and then it puts it creates a hash where it says that this ref points to this object. So it's really just building the map as a memory in-memory data structure in Go. So those are the new refs, and it's possible that there is no pack file at the end if nothing changed. So we need to peek and see if we see the magic header of a pack file. And if it's there, then we boot up an index pack process. And index pack is actually very important to this. And this is also one of the interesting trade-offs in this system, because the pack data on its own is useless in Git. If you have a pack file, if you just have the .pack, you can't do anything, because it doesn't even contain the, you can only traverse it by going through it sequentially, and it doesn't even contain the SHA-1s of the objects in there. So index pack will actually look at every file, every delta compressed object in a pack file, and compute its SHA-1, and then build an index saying, well, if you have this SHA-1, go to this offset in the pack file. So until you have that index file, you don't even know what objects you have. It's really a crucial part of how the pack file format works. And I don't know exactly why the Git authors designed the transport so that the index file doesn't get sent over the wire. Maybe it's because you can reconstruct it from the pack file, or maybe it's because you might not trust the server. I'm not quite sure, but things will be much slower creating the snapshots if we had to create the index file at the same time. So we don't do that until we do a restore. So this thing is reading and verifying the whole pack file that was in our storage and creates a pair. Let's look at that. So this is my repo.git, and if I look in the objects, where am I? Oh, I forgot to create a bare repo. Not smart. So if we look in here, then you see the every pack file has an IDX companion. So these get created on the restore side, and that if it's a large file, that will take time. And this is also what happens during a Git clone. If you do a Git clone, you see a whole bunch of receiving objects where and then it was resolving deltas and whatnot. That's all index pack, processing the data, the pack data that was sent by the server and building the corresponding IDX file. So we run index pack, and then we still need to update the ref database. And for that, we look at the current refs just by running git for each ref. And we turn that into a map. And then we have a map old refs and new refs. We do a simple loop where for every new ref, we say this thing must exist. So we create a command that says update that ref to this object ID. And then we loop over the old refs, and if they're not found in the new refs map, then we add a delete command for update ref. So we delete everything that no longer exists according to the new refs, and we feed that as one big transaction to git update ref, and that updates the ref database. And that is the end of the restore process.
That seems quite straightforward.
Yes, that's one of the reasons why I like this. It's actually, yeah, it is straightforward. And I sort of came up with this because I was trying to think about sane ways of storing repositories in object storage. And ref database is what makes everything so hard. And if, and this is a very, very naive and simple way to store the ref database. You just store a complete dump of the ref database, and like if one thing changes, you have to do an entire new dump, which is not the most efficient thing to do, but it makes things much simpler, and it allows us to just get this fairly simple data structure where you just need to know this sequence of blobs.
It seems like it's pretty well optimized for I guess like what you're saying is like it's well optimized for efficiently writing incremental backups.
Yeah.
Yeah.
If you want to make your restores faster, you can make a variation where you can have two types of binary payloads. So you could either have a pack file or you could have a tar file that contains both a pack file and an IDX file and a bitmap file. And then you could sort of hit the ground running if you unpack that. But for this to be sane, a system like this to be sane, you need to clean up this log, because otherwise, if you just keep adding these log entries, at one point you have 1,000 of these things. When you unpack them, you're going to have 1,000 little pack files.
Yeah.
And Git doesn't like that. So you need a continuous process running next to this that compacts this. And I can show what the compaction looks like.
Have you implemented that as well?
No, I could just show it in a shell. Let me just, for sanity, this is, by the way, another interesting problem. If you want to do this compaction, you want to sort of know that nobody else is doing stuff in this repo you're working on. That's why I just rmrf'd it. So let's create the bare repo. Repo.git. And now I can do my fancy thing with find. see, does that work? Oh, I want to remove this thing because this was just some debug output. So okay, sort that and then snap in. This is a funny shell that I use. Let me make this a bit bigger. So I'm now creating the list of all these things in sorted in alphabetical order, and I'm going to do Gitaly bundle apply out of that thing. And I hope I got that right. Yes, and there were only 2 pack files here because I made one snapshot where there were no new commits. And for compaction, I would now do okay, there are two angles. So this idea, what I said, where you store both the pack file and the IDX file for efficiency, we don't have that, so I'm not going to do that.
Mm-hmm.
But what I can do is I can do a Gitaly bundle create from dev null, meaning that there is no existing data that we are building on, and I can create .storage repo.git, and I'm at level 002 because I know that was my. I'm doing a compaction at level 002.
Mm-hmm.
I can call that full. And now we have this new one here. And then we could say we remove the 0, the 1, and incremental.
Yeah. It seems like this could be something that's run similarly to like the garbage collection, which happens every 100 pushes. Like we could just repack every 100 pushes.
It is literally, that is also just running Git back objects.
Yeah.
So it's very similar. The downside of something like this is that the index back will be slow. So one thing that I can maybe show as a last example is what this looks like if your repo is bigger. And I hope that I can clone the repo fast enough. So I need to reset stuff. I'm going to remove this here on the replica. And I'm going to clear the storage. I don't need this. I'm going to ignore this user thing. And I'm going to remove this one. And let's take GitLab CE. This is a perfect way to get jinxed. I mean, cloning a large repo in a video demo, like what can go wrong?
While we're waiting, that's pretty fast. I was going to say, while we're waiting, do you have any thoughts on the applications for this?
Well, the motivating idea is this epic that Sid created about storing repositories in object storage. So it could be a form of cold storage. I don't know how practical that is because this system is asynchronous by design. So the snapshots are always going to lag behind the last write. So it's sort of a difficult. But the technical question of how much are they going to lag, and there's the business question of are we happy with a system where there is this lag? A different application, which would be very sensible, I think, is streaming backups. Native streaming backups at the application level, because GitLab does not have a very good story for backing up repositories. You can either make a backup of everything with a rake task, which is fine if your GitLab server isn't too big, because then you can afford to create a big tarball that contains a second copy of all your data. But that is completely unusable on gitlab.com. So now we're looking at index pack, computing all these SHA-1s. Actually, I don't know if that's literally what it's doing right now, but it's part of what it's doing. So for gitlab.com, we solve repository backups outside of the application. We solve it at the infrastructure level by using file system snapshots or block device snapshots or both. And I don't know how this all works for self-managed installations where people have a lot of data and where they're too big to be using the rake task. So there's sort of a gap there,
Yeah.
you could say, from a product perspective. And with something like this, you could build a system where you have a continuous thing going on somewhere in the application that scans through projects that recently got modified and creates new backups and compacts them and keeps track of how many snapshots there are. Because when you do a restore, you can choose how far you go.
Mm.
So this could be a type of backup where you can also if you just do replication and you delete stuff, then at some point you're out of luck. But in this case, you have a replication log, and if you have enough log data, even if you deleted stuff, you can still go back to a previous log entry where stuff is not deleted.
Mm. Yeah, it gives you the ability to restore to specific states, not just to.
Yeah, and with the compaction, you can also make a choice, because in my example of compaction, I compacted everything, but you can also say if I have 100 snapshots, or I only compact up to a week ago, and I leave the snapshots between a week ago and now in the storage.
I wonder if there's an application for replication with HA. I know that, well, from what I understand with the HA architecture currently is that prefect will simply just mark the other nodes as stale, and then those nodes will fetch from the primary node that's up to date. Is that correct, Paul? Yeah, you're nodding. I'll take
Yeah.
that. Like in theory, if that's like a relatively low number of replicas, that's probably fine. But if we were thinking about a future state where we have geographically distributed replicas and a high number of them, so say like 5 or 7 replicas or some sort of significant number for a large project.
If you need to do
Every
a fan
time you
out,
do,
this would enable a fan out, because you can write these things. This is the, it's not literally the same data, but this is the same data that has to go across the network if you would do a git fetch on a secondary.
Exactly. Yeah.
And yeah, if you need to do a fan out to multiple secondaries, you could put all this stuff in object storage, and then they can read from there.
That's what I was getting towards. Is like it takes the read load. Like every time you write to the primary, then you're creating a read load on every other replica that's going to hit the primary simultaneously as soon as they see that they're out of date.
Yeah. Note that me creating the initial snapshot here is taking about as long as a clone. Maybe I should have timed that.
I imagine subsequent, like it's essentially the equivalent of like excluding the first time you generate the thing, the incremental ones is essentially doing a fetch immediately after, right?
Yeah, it's a clone and it's a fetch. That's really what it is. I mean, another way to describe this idea is that we are taking some of the data that Git sends over the network during these operations, and we just freeze that data in a file, and we throw that file in object storage so we can replay it later. It's not literally that, because the Git transport is more flexible. So you could try and implement a complete Git transport, because you can have pluggable Git transports, or Git remotes, I should say. But that's more work, and this is less work than building a fully fledged remote. But yes, clone fetch. That's literally what this is. Let's see if there's some new data already. Are people pushing branches? No, they're not. Okay, there's another thing we can do. Well, I could just clone it again here and do my thing with the user commits.
I was thinking about like increasing the use of object storage. I think one of the things that I think this is a challenge we've spoken about before, is it's hard to use object storage for like the actual primary. Like I think that like there's, depending on the epic or question you're referring to, there was discussion at one point about literally using object storage for the primary, right?
Well, but that is much harder, because then you need to Git itself doesn't let you do that. So Git expects that there's a file system where it can open these spec files, and you have alternative implementations of Git like JGit and libgit2, where there's an abstraction in between Git saying, I want a PEG file, or the library saying, I want a PEG file, and literally looking for it on disk. So if you use a library like that, you can create this abstraction layer where you fetch it from object storage instead. And I believe that's what, I saw a presentation somewhere where someone from Google said that that's what they're doing. But that is on the scope of rewriting all of Gitaly to use a different Git backend.
Correct. I just wanted to clarify that that is like a different problem. I guess
it is a very massive problem to do that. And there's also a technology question there that what I saw in the Google example was that, let me just look for that for a moment.
I guess the other thing just to raise, like having recently messed around with storing lots and lots of small objects in object storage for a side project where I was storing 100,000 objects that totaled less than 50 megabytes of uncompressed data. I got a non-trivial AWS bill. Like, I mean, it's still in the magnitude of like single dollars, but for like very small data transfers, reading and writing lots of small objects, if you're using a commercial cloud solution, is very expensive because they bill on those. So
on the requests count.
Yeah. So that would make it almost cost prohibitive to use object storage as a data store if you were just storing loose objects in object storage.
Yeah.
At that point, then you need a local scratch disk to or hold stuff in memory, and neither of those are practical for large projects that have high degree of activity.
No, so I think, so this is the presentation I'm talking about, which is from 2013. I don't know if it's accurate anymore, but what they say here is that they store references as rows in Bigtable, and well, Google has Bigtable, but as the average GitLab deployment does not have access to Bigtable.
Yeah.
And then I think they say the PEG files are on GFS, which is some sort of quasi file system. It's not quite a file system, I think.
Is that Gluster or?
I don't know exactly what it is. It's one of those internal Google things. Distributed file system, so it might be Gluster-like.
It's interesting though that on that slide they immediately mention that they're not storing loose objects; they're storing small pack files of like a couple of megabytes.
I don't know exactly how they did this, but I think one big part of what they're doing is that they're using JGit, and JGit has JGit has pluggable storage. So the hard work. If we would have built our thing on JGit from the start, then we could be talking about pluggable storage, even though this idea of having a massive database for all the refs of all the projects, I'm not so sure. Like,
there is a native Golang project, isn't there, where for like a Golang equivalent of JGit, or is it a Golang wrapper of libgit2?
You have both. I know that libgit2 supports pluggable backends, but I think that has to happen at the C level. I'm not sure if Git2Go, sorry, not Git2Go. You're talking about GoGit. So GoGit is a native Go library implementation of Git, and if they have pluggable storage, I don't think they have pluggable object storage as a plugin. Sorry,
I think they have pluggable plumbing, right? Like everything in their plumbing can be customized.
Yeah, they made that library for a very specific purpose. That's because they want to do huge analyses of Git repositories. So they have a backend where a repository gets stored in memory, and they can run statistics and search for interesting patterns in it quicker. But they're not into GitHub.
This is a bit of a tangent from what you.
Yes, it is a tangent.
So, maybe to bring it, maybe we should try and bring it back to some more practical things. I think the native stream backup is something that we should probably create an issue about and start talking with the infrastructure team, because I know that's a problem that we have, and no doubt our customers have. There likely are already issues about this in the issue tracker.
Yeah, it's. I don't know how many people are actually asking for it, right? Because it's the infrastructure team is not literally asking us for this, because they're building auto backup solution based on file system snapshots, or they're iterating on that that approach. And I think from a time scale perspective, they want to do that anyway, regardless of whether we can create a streaming backup solution. So streaming backup solution is also maybe a solution looking for a problem or looking for someone who wants it.
That could be the Geo team.
Geo is another interesting example, because another nice thing about having something like a log is that if the secondary falls behind, the primary can keep writing these log entries. And sorry, it might be a nice way to, a saner way to do replication. Although they built replication based on git fetch, they got that working. So I don't know if there's a real need there for a completely new replication mechanism.
Just so I understand how this could be potentially used to save storage costs. If we had a repository that was being read a lot but not written to very often, would it be possible to serve it directly from something like S3, or does it still have to be brought down?
No, it has to be brought down. That's this problem that, like, if we would have written everything in JGit, and if we had GFS, which is apparently Google file system is apparently good enough, or was good enough in 2013 for Google. If we would have built the entire thing on technology like that, then we could do that. But we didn't. So we chose using native Git. So we need a local copy of the repo on a file system, whether we need to serve reads or writes. For writes, the problem is that we have all sorts of events that happen immediately after your write. So you want to be able to read your own writes, or read. There should not be a lag between a write coming in and showing up in the readable copy of the repo. And the easiest way to do that is to say that there is a single disk copy of the repo that receives the write and fires off hooks, and that we then replicate later. Yeah, to circle back to my opening, this is a solution looking for a problem. But I thought it was a cool idea and I wanted to share it with you. So thanks for letting me ramble about it.
I think it's very interesting.
Thanks.
I think it would be worth Paul, ZJ's not on this call, but having a discussion around the relevance of this to high availability and the replication method chosen there, because unlike Geo, we haven't actually implemented the fetch replication yet. And
I think we have, or we have a first version of it.
Yeah, it basically does a internal fetch, or yeah.
Yeah.
Okay.
It does the equivalent of this, except using RPCs we already have.
Okay.
And the data that here I'm putting in a blob temporarily is just going across the network once and being consumed, and then it's gone.
Okay. Yeah. So this could be then considered just a performance optimization that delivers it. I guess it solves the, like, if we implement it in a certain way, it could solve the streaming backup at the same time as solving like fan out performance.
Yeah, perhaps.
And then that could lead to potentially a refactor for Geo as well. So there's like a standardized replication methodology used everywhere.
Yeah, again, I don't have a very clear story of what this is for. And there's one other thing I need to mention, that one other thing that is important to keep in mind when we compare this with what we already built for at the current stage of Gitaly HA. Object storage does not do locking of blobs, and it's very important that these blobs get written by only one writer. And there will be potentially multiple places that can try to write this. So you need a form of coordination outside of object storage to make sure that only one thing is creating a new log entry at the time. And that could be done with SQL to create a kind of locking structure, because then the SQL would work across machines and across processes. But it is a crucial moving part, and that's not part of this demo because I'm just picking these numbers here by hand, and I'm the only one running the commands. But in a real system, we can't make such assumptions.
That is a good point.
If we had multiple people creating objects, snapshots, and there's a way to identify them by the content of like the refs that have changed or something like that, we might be able to reconcile them after the fact, right?
Yeah, but the problem is that yes,
there just might be a lot of wasted effort in doing the same content at the same time is probably one of the issues related to that.
Well, if you have multiple, so this thing is like a clock, right? 0, 1, 0, 2. So if you have multiple entries for the same clock, you could say that you take the union, you take all their ref dumps and you combine them and you unique them and you say, when creating the next snapshot, let's presume we have all of these. So you could do a fan out that way. One problem is that it would be somewhat arbitrary. Okay, here's a problem. When there are concurrent writes in Git itself, Git somehow resolves that. It uses the POSIX file semantics to somebody wins the race on the update of the ref database, and then that's what the user sees. And the problem is if we allow these forks, these divergence to happen in the storage thing, we don't know who won the race. So it might be that when we restore this, somebody else won the race.
Yeah, because it's not serialized. That makes sense. Yeah.
And if we restore at a point where everything converged anyway, then we don't care. But if we restore at one of these spots, then we return the repo in an unexpected state.
Yeah, that makes sense. We need coordination to do this.
Yeah, probably.
Yeah.
I mean,
that
and
could be coordinated by prefect, though. Prefects are going to have a coordination problem anyway, right?
Yeah, I mean, as long as someone owns the repository and can coordinate these actions, it should be. It could be handled there.
Yeah, I also expect, and you know better, Paul. I also expect that prefect will have a coordination problem because it should be possible that it should be expected that more than one prefect process is running and providing access to the same resource. Because otherwise, if there's a single prefect process that everything has to go through, that would be a single point of failure.
Right now, that's what we're accepting for the current iteration.
Yeah, for the beta. Yeah.
Yeah, but eventually, yeah, the idea is we'd have to mesh that out somehow so that other prefects can handle the traffic for a specific storage location and repository. But right now, that's one of the single points of failure that we're accepting.
Yeah. So I think coordination is just a general problem that we're going to have one way or another. So in that regard, it's a downside of this cute story I tell you, where there's just a bunch of blobs that you need to add coordination on top, but it is a somewhat normal requirement. Any more questions?
I just want to put a little comment in there. I like that you put the stuff in the shell scripts because it's it's much more readable that way, and it's more universal and accessible. So I like that.
Thanks. Okay. Yeah. I don't know if everybody likes awk as much as I do, but
thing is, everyone's got it right on their machine.
Yes.
So that I like that about it. It's low friction. It's easy to get running on anyone's machine. So I think that's cool. I like that approach.
Thanks. I don't think I would use it for production code, but in this case, for prototyping, it made sense. Okay, well, let's wrap this up. I'm going to see if I can click the right button to stop the recording. Bye-bye to the viewers at home. Do you want to stop cloud recording? Yes.